this video, we take a closer look at inductor characteristics. We have mentioned before that once current flows through the inductor, a flux will occur immediately. Let's say we connect our inductor to a voltage source via a resistance R. This circuit is called a series RL circuit. Now, without showing the derivation, the current that we will get there will increase gradually, and in fact will behave exponentially as shown by this equation. Since our flux is directly proportional to the current that flows through it, that means that the flux will also behave exponentially and will be given by this equation. This equation tells us that the rate of flux buildup in the inductor varies inversely as the magnitude of R. That means if R is high, we will have a slower flux buildup. If it is smaller, we will have a faster flux buildup. For the series RL, the rate of flux buildup decreases as the current rises until it ceases or stops when I becomes a constant at V sub S over R, at which point the circuit is said to be at steady state condition. Let us try to differentiate equation 1 that will give us this equation. And let's do some rearrangements. We will notice that this expression on the left gives us the voltage across the inductor. We call that voltage and induced voltage taken from Faraday's law. Thus, we have a very important relationship between the voltage of the inductor and the current that flows through the inductor, as shown by equation 3. This equation tells us that the voltage across the inductor is proportional to the time rate of change of the current through it. Its polarity is such that it will oppose any change in the current. For a series RL, if we substitute the current that we derive or the current that we've shown earlier, the voltage that we will get across the inductor will be given by this equation. Equation 3 shows the relationship between the voltage of the inductor and the current through the inductor. But it also tells us a lot more. For example, it shows that the voltage V sub L, the magnitude of that voltage, is proportional to the time rate of change of the current. The higher the time rate of change, the higher will be the magnitude of that voltage. The lower time rate of change, the lower will be the voltage. It also tells us the polarity of the voltage. For example, if the current is increasing, that means that the IDT is positive, and therefore the polarity of V sub L will be it is plus here, it is minus there. Also, if the current is decreasing, that means that the slope must be negative, and therefore the polarity of V sub L must be, it should be plus here and negative there. Further, it tells us that the current through the inductor cannot change abruptly. What do we mean by this? So let's say we have a a plot of the current through the inductor versus time, and let's say the plot looks like this. So at time t sub 0, it changes from a certain value to 0 abruptly. According to equation 3, this is not possible because the slope here is infinite. So that means this is infinite, and that means we will get a very, very large voltage, which is not possible in practical terms. Also from equation 3, if we're given the equation for V sub L, we can actually solve for the current by doing integration. We could also compute for the power and energy of the inductor. So power is always VI, but we know V of the inductor to be L di dt, so we could substitute for that expression for V sub L. For the energy absorbed or released by the inductor, we could integrate the equation of power from one time instant to another time instant. That would give us an equation which is 1 half Li squared. So how was this derived? So we know, so energy is P times dt, but we know P to be L. So this is I di dt times dt. So dt will get cancelled. L is a constant. Integral of I di, that will give us 1 half I squared. So therefore, energy would be 1 half Li squared. Okay. So if current changes, that amount of energy that was stored or released by the inductor would also vary. At any given time, the state of an inductor can be classified as either a transient state or a steady state. A transient state means that the voltage and the current of the inductor is changing over time, while a steady state means that its voltage and current is either a constant, which means it is not changing, or is a zero. Now, what is interesting about an inductor that is at steady state is that the voltage across it is a zero because the current is a constant. That is, if we get a derivative of a constant current, that will give us a zero. So this one will be a zero at steady state. So therefore, V sub L will be a zero as well. Now we know that if an element has a zero voltage, that means that it is like a short circuit. A circuit containing an inductor that is under a transient state or undergoing changes is said to be in a transient state itself. That means the voltages and currents keeps changing, while a circuit containing an inductor that is in steady state is said to be in a steady state condition as well. Now sometimes a circuit that is under steady state is said to be in a DC condition. A circuit in steady state can transition to a transient state if it is disturbed by external forces, like, for example, a change in voltage, a change in resistance, and many more. But if those changes stops or ceases, the disturbed circuit will eventually settle to a new steady state condition.